So we also want to talk about a distribution when we have some sort of a sample mean that is not a normal distribution or doesn't come from a normal population, in other words. We've looked at this image before, but let's talk about it one more time. So this is talking about the probability distribution for the cumulative number of children for women who are 50 to 50 years old who've had births. And you can see that the distribution in what we're looking at here is obviously skewed right. So this is a discrete variable, but once we start looking at the histogram of it, we have over here the distribution when we have a sample size of 3. Then we notice that as we start to increase the size of our sample, so we went from sample size of 3 to a sample size of 12 and ultimately to 20, we can start to see that the distribution of this population starts to become more normal in its distribution. And so that is basically what we would think of as the central limit theorem. So the central limit theorem says that the shape of the distribution of the population from which our sample is drawn is going to dictate the size of the sample that's required for the distribution of the sample mean to be normal. In other words, depending on how skewed your population is to begin with, that's going to dictate the size of n to make it approach that normal distribution that we would be looking for. The more skewed the distribution of the population, the larger of the sample size needed to invoke the central limit theorem. In other words, if the distribution of the population is unknown or not normal, then the distribution of the sample mean is approximately normal, provided that the sample size is greater than or equal to 30. If I don't know what the original population size was, if I don't know what I mean to say is if I don't know if the distribution of the population is unknown or not normal, then it's basically just we're going to start using the number 30. If you can get to a sample size of 30, then you can pretty much guarantee that no matter what your population's distribution was, it will become normal for us to be able to utilize it. So again, the mean and the standard deviation of the sample distribution is going to be the same for both normal and non-normal distributions. So the previous example that we talked about, what we did in that previous example is going to be the same concept as what we're going to do moving forward, as long as we apply that central limit theorem. Or in other words, as long as the sample size that we're looking for is greater than or equal to 30. So what I want to do is I want to look at, and again, just to highlight our central limit theorem, that regardless of the shape of our underlying population, we would say that the sampling distribution of our mean, which is x bar, becomes approximately normal as the sample size n increases. So let's look at an example then. We have here that the weight gain, the mean weight gain during pregnancy is about 30 pounds and with a standard deviation of 12.9. Weight gain during pregnancy is skewed right. So an obstetrician obtains a random sample of 35 low-income patients and determines that their mean weight gain from these 35 low-income patients, he determined that their mean weight gain during pregnancy was 36.2 pounds. So we want to see if we can figure out, we want to be able to say, does this result suggest anything unusual in what he's looking at? So what are we given? We know that a couple of things. I know that the mean weight gain is 30 pounds. The standard deviation is 12.9 pounds. I also know that weight gain is skewed right, so it doesn't come from a normal distribution. Then we come on, so let's write down a little bit of that information. I know that the mean is equal to 30 pounds. I know the standard deviation is equal to 12.9. I know that this is skewed right. The next thing that I'm told in this is that this doctor took a sample of 35. So the sample size now that we're looking at, n, is equal to 35. And he determined that the mean weight gain during pregnancy was 36.2 pounds. So we want to know if that's unusual. So what is the probability of getting a pregnancy, right? What is the probability that out of 35, a sample size of 35 patients, what is the probability that the average weight gain is going to be greater than 36.2 pounds, which is what he had happen in his single sample? Now, because the sample size is 35, even though we are looking at a distribution that is skewed right, since the sample size is 35, we can go ahead and use that normal model. The next thing that we want to be able to identify is that since we can use that normal model, then we would say that the mean of the sample is the same as the mean of the population, or in other words, we're going to use a mean of 30 in our calculator. The next thing that we want to be able to put into our calculator is the standard deviation of the sample. The standard deviation of the sample comes from the standard deviation of the population, which was 12.9, divided by the square root of the sample size, which is 35. Plugging this value into my calculator, I find out that 12.9 divided by the square root of 35 is going to be 2.1805. Let's use those values and plug them into the normal calculator. So remember that in StatCrunch, to use the normal calculator, we go to Stat, Calculators, Normal, and the mean that I'm interested in here, which was given to me as 30, because the mean of the sample is the same as the mean of the population. The standard deviation that I'm going to be using is 2.1805, and I want to know, is it unusual what's happening if I have pregnancies that are coming back with a weight gain of greater than 36.2. And you can see here that the probability of me getting a sample where weight gains are greater than 36.2 is approximately 0.0022. Approximately 0.0022. So I'm going to put that down in here. So what does that mean? What exactly is this question asking? Well, if we were to interpret this probability, it says that if the population from which the sample is drawn has a mean weight of 30 pounds, then the probability that the random sample of 35 women has a sample mean weight of 36.2 pounds or more is only about 0.002. Or in other words, only 2 samples out of 1,000 would result in a sample mean of 36.2 pounds or higher if the population is 30 pounds. So from that, we can basically conclude two things. That the mean weight, and let me make this bigger, we can conclude then that the mean weight for those low-income patients is 30 pounds, and what this doctor happened to select were women who on average gained more weight, because it's unusual for you to even come up with a sample having that result. We can also conclude that the mean weight gain for low-income patients is more than 30 pounds. Those are two of the things that we could conclude. Now, if you notice right here, it says that we are inclined to accept the second explanation over the first because our sample was obtained randomly. In other words, this obstetrician should be concerned, or in other words, perhaps she should look at the diets and or lifestyles of low-income patients while they are pregnant. So the mean weight gain of low-income patients is more than 30 pounds is the resulting idea that they got out of this.